Hi guys, I wanted to make a very short video on something called the apparent depth part of this optics lecture. People are finding it slightly difficult to solve questions on apparent depth, so I thought I'll make some additional video on this. So to understand apparent depth, let's quickly go through some part of the theory and then let's do some subsequent questions to reinforce the concept. So for that, first thing I need is a glass slab. Let's say I have a glass slab right in front of me. Okay, and the reason for this apparent depth or the reason that the images is formed little bit elevated from the bottom of a lake or something denser is because of a refraction. Okay, so I want to make some normals here. What I'll do is I'll draw some lines. Okay, I'll draw some lines. Let me insert some lines here. So let's say I have like let me hold down shift. Let me change the color as well. So let's say where is the yep, this is my first normal. Okay, so let's say there is an object which is kept at the bottom of this particular glass slab. Okay, or whatever this medium is, maybe this is water, so I'll write like mu2 here and let's write mu1 here. Please understand, mu1 and mu2, I'm not specifying water, glass, anything here because I just want a general case to begin with. Let's say I have something at a depth of d, like this distance right here, let's say is d, right? Now when I make the rays for this one, like the actual rays which are coming out from this, it will come like this, let's say. Okay, and let me make another normal right here. Somewhere around here is the next normal. Now as it is going from a denser medium to a rarer medium, it bends away from the normal like this, right? This is how the ray actually travels. On the other hand, when we look from this side, like when we actually use our view to essentially look at the image of this, we don't see this refraction happening. We just see okay, maybe the object is right here. That's like the image of this particular object which we are seeing from here. So this is actually known as the apparent depth, d dash. Okay, this is the apparent depth. Now how do you find out this d dash? We first of all, you have to understand the apparent depth formula again takes into consideration the basic sort of assumption that we have been always working on, that is the fact that the angles are really small. Okay, so if I say that this angle is angle of incidence and this is the angle of refraction, from geometry I can say a few things about these angles. Like for example, this angle right here is also r. Now that's because alternate interior angles, these two lines are parallel, the two normals that I have drawn are actually parallel, so these two angles are alternate interior angles. This angle right here is actually just I because corresponding angles, again two parallel lines, corresponding angles. And if I say that this distance from here to here is let's say x, then few things I can say about this particular diagram. Let me move it sideways a little bit. Okay, is that the first thing I can say about this is from Snell's law is mu1 into sine I is equals to mu2 into sine r. Okay, now this is a very big if. Okay, so if the angles involved, okay, if the angles are small, then I can write that sine I is essentially just equals to tan I. Okay, now this is very strong, and also this is very true only for small angles. Okay, that sine theta becomes equals to theta, and it also becomes equals to tan theta, right? How does it help me? Well, if I write mu1 into tan I and I say that this is equals to mu2 into tan r, okay, tan r, and I look at these triangles right here. Okay, so I'm gonna point out some triangles right here. Like for example, look at this triangle, like this triangle right here. Here you can see this is the angle r, and opposite is essentially x, but the adjacent side is d. So if I plug in the values in this triangle, trying to define tan r here, tan r is perpendicular by base or opposite side by adjacent side. If I plug in the value, tan r is nothing but x divided by d, right? And similarly tan I and tan I will be able to identify in this particular smaller triangle, smaller right triangle here. It is again 90 degrees. So if this angle is I right here, the opposite by adjacent will mean that I'm looking at something like x divided by d dash, which is like the apparent depth, right? So from here d dash comes out to be mu1 by mu2 into d. Now this is very, very powerful. Okay, you're telling me if you know the refractive index, if you know the refractive index of the two mediums, and you also know the depth at which the object is kept, you can find the apparent depth by simply taking the ratio of those refractive indices and thus multiplying the actual depth, and you get d dash. Okay, so what I want to talk about next is something called the shift. Okay, the shift. Okay. Now you have understood what exactly apparent depth is. The body gets elevated, right? But elevated by how much value is known as shift. So in here in the diagram, if I show the shift, this is the shift. Okay, this is delta H. Okay, it's the amount by which the object was raised when it became the image, right? So that is what is known as the shift, and that delta H is actually nothing but something like d minus d dash. D minus d dash. Now we have already figured out how much d dash is. Now that is just d minus mu1 by mu2 into d. Okay, d dash is mu1 by mu2 into d. Now that is equals to d 1 minus mu1 by 2, right? But if mu1 was, let's say, 1, like if you're doing it with respect to air, then the shift that happens in the upward direction because of a particular glass slab is nothing but d 1 minus 1 by mu. Okay, so if you have a material, whose whose depth is d, okay, and it is made up of a refractive index mu, so the shift that it can create is equals to d multiplied by 1 minus 1 by mu. Okay, now the portion in which the people are facing a difficulty is not the apparent depth itself, but it's a scenario when you have multiple different slabs, right? Something like one slab on top of another slab on top of another slab. Let me also change the colors right here. Okay, so you have like 3 slabs. Let's say this slab is of thickness d1, and let's say this is thickness d2, right? And let's say this is of thickness d3, right? And let's say we keep something at the bottom of this slab, right? And let's say this is mu1, this is mu2, and this is mu3. How would you find out the apparent depth of something that is kept at the bottom of 3 different layers with 3 different refractive index? This is where people are struggling right now, right? So how do you find that one? Is actually pretty simple. You say that the net shift of the object in the upward direction will be the shift because of the first layer plus the shift because of the second layer and the shift because of the third layer, right? So this is something that I wanted to tell you. Okay, and finding out the shift because of each one can be done by using the formula that we derived in a bit. So you can pretty much treat like the shifts because of individual layers separately, and the net shift will be just the addition of all of this, right? So that would mean delta H1 would be just D1 multiplied by 1 minus 1 by mu1. That will be the shift because of the first layer, right? What about the shift because of the second layer? You just multiply D2 with 1 minus 1 by mu2, right? and the shift because of the third one would be d3, 1 minus 1 by mu 3, right? So this is something that I wanted to tell. If you are dealing with a question which which has an object at the bottom of 3 different layers, and if you want to find out what is the net shift in upward direction, you can add all the individual shifts because of each layer. Had this layer been just there with air, like if you treat them independently, like one layer in air, mu2 layer in with air, and then mu3 layer with air, you find out all those shifts, and the net shift will actually be just the addition of all of this. So sometimes they may also ask you what is the new apparent depth. Now if you already know the net shift in the upward direction, let's say, is delta h net, then the apparent depth d dash can be just found out by you adding all these values d1 plus d2 plus d3 and just subtracting like delta h naught from it, okay, delta h net from it. So if you are looking for apparent depth in a scenario when you have multiple different layers, this is the way to go. Guys, I have a question based on this particular concept. So the question says there is in the bottom of a container is a stone, and there are 2 layers. One is the glass slab of thickness 4.5 centimeter, and over it is another layer which is made of water, and its height is 8 centimeters from the glass slab, right? So the question is, what is the apparent depth and what is the effective refractive index? So pause the video and try to do it on your own. If you can't, look at the solution that I'm going to do, right? So the values of refractive index and glass are also given. So let's see if we can essentially make the diagram for this. So well, this is how the first layer would look. This is like the layer of water, and you also have like the layer of sorry, the glass layer is at the bottom, right? So let me just make this one gray, right? So this is like the glass. So here it's the refractive index is given to us as 4 by 3. No, it's given as 1.5, and this is like the water on top of it, and that is 4 by 3, I believe, right? Yeah, it's given as 4 by 3 and 1.5. So there is something, there's like a stone at the bottom of this, and we have to figure out where the what will be the apparent depth, right? So we know that the net shift in the upward direction will be the shift because of glass and the shift because of water. Now the shift because of glass would be something like given as also the thickness is given. So this is 4.5 centimeters, and this right here is actually given to us as 8 centimeters, right? So we have to plug in the values here. Let me just move it slightly this way. So that is going to be like 4.5 centimeters into 1 minus 1 by 1.5, right? So this is the shift. I'm just using the formula that I derived like few seconds ago, and plus this is going to be 8 centimeters into 1 minus 1 by 4 by 3, right? So if I do the calculations here, I think it's 3 by 2, so 1 by 3, so it's going to be 4.5 by 3 plus 3 by 1 minus 3 by 4 is just 1 by 4, so 8 by 4. So I think this is going to be 1.5 and this is going to be 2. So there's going to be a total shift of 3.5 centimeter from the bottom, right? So the net shift of the object is actually 3.5 centimeters, whereas like the actual depth, like the total depth of this is just 8 plus 4.5, so that's like 12.5, right? And it has shifted up by a distance of 3.5, so the apparent depth is actually going to be 12.5 minus 3.5, so that puts me at 9 centimeter, I believe. So the answer to your question is going to be, let me check the answer. Yeah, 9 centimeter is the correct answer for this one, right? So you found out D dash. Now what exactly is effective refractive index? Well, it's something like if this was like a complete one material, what will be the refractive index of that material so that it will have the same apparent depth? Let me repeat one more time. What exactly is effective refractive index? If instead of two layers, if you had like a single layer of one material, what would be its refractive index so as to create the same amount of shift, or so as to create the same amount of apparent depth? Now that you can directly just assume key, imagine if this is one big material with mu, then mu is essentially just d by d dash. Just look at the previous formula that we derived. Okay, for a single layer, like this was the derivation done, d dash is nothing but mu1 by mu2, but here we're considering to be air, so air 1 by mu into d, so d by d dash is essentially mu, right? So d by d dash is mu. So d we have found out is 12.5. This is the real depth, and the apparent depth is 9. So this ratio is going to be your answer. I believe this one is close to 1.4, approximately 1.4. So if you had to imagine a single layer where the single layer would have the same apparent depth, that refractive index is going to be 1.4. So guys, this is how you do questions with multi layers of so guys, this is how you do questions which has multi layers of material that has different refractive indices, right? So this is how you approach these kind of questions. I'll see you in the next video.